Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is again give an example here of how to use a graphical method to analyze the motion of an object. So the object we're going to analyze here is this car here, my favorite little race car. And in this example, imagine this fellow's driving down the road. He's driving 80 miles per hour, maybe down a highway or something, and he sees 250 feet out in front of him a cow, right? So he applies the brakes. He wants to be a little careful here. The cow's maybe not on the road, it's on the side of the road, but he wants to slow down and be a little bit careful. So he applies the brakes, and over 250 feet here, he slows the car down in such a way that he's still going 65 miles per hour when he goes by the cow. So again, in this problem, it's the car that's changing velocity. This cow is just sitting here stationary. So the first thing I'm going to do is maybe draw a velocity vector here for the 80 miles per hour, and maybe call this like maybe V initial or something. And then second, I'm going to draw another velocity vector here to represent the 65 miles per hour and maybe call that V final. Now you notice that I try to draw that a little shorter. That's because 65 is less than 80, and the length of the vector is representative of the magnitude of the speed. All right, the 250 feet is labeled. Now, again, if you've seen my videos on analyzing motion, the velocity graph is the one that tends to be, I believe is the most useful here. Once you have the velocity graph, it's kind of a one-step process to both acceleration and displacement information. So just going to draw a quick sketch here. Now, again, we're going to graph velocity against time. All right, now, before I draw the sketch, I'm going to take note here of units. Now this is in 80, this is in mile per hour, same thing here, mile per hour, and this is in feet. I'm going to go ahead and use kind of standard English units, which would be feet and seconds. So the very next thing that needs to be done, the next thing that needs to be done maybe is unit conversion. Now I've already done the conversion. Hopefully you've seen my videos on unit conversion. I'm going to go ahead and just write down the results. 80 mile per hour is 117 feet per second. Okay, if you don't know where I'm getting that from, go back and take a look at my video on unit conversions. And in the previous motion video I did, I wrote the conversion out. But this one I'm just going to move along here. The 65 mile per hour is 95.3 feet per second. I can write that a little better. Feet per second. All right, so at t equals 0, the car is going 117 foot per second. Sometime later, and I don't know a time yet, our delta t here is unknown. That's going to be one of the unknowns here. We'll deal with that. But sometime later, the car is going 95.3 feet per second. I'm going to put a coordinate system in, as usual. Anytime you're dealing with vectors, you should put a coordinate system in the problem. So I usually put my coordinate system wherever the start of the problem is. So I'm going to call this t equals 0. I'm going to go ahead and put the origin right there. X, Y. And again, important to realize this coordinate system isn't going anywhere. It's fixed there. And then the car moves to the right, and then its x coordinate will be getting larger and larger and larger. All right? So this is just a coordinate system, x, y. All right, now, at t equals 0, this car is going 117 feet per second. I don't have a scale yet. I'm free to choose whatever scale I want. I'm going to go ahead and just put that 117 up here, 117 feet per second. Sometime later, we don't know the time, and again, I'm free to choose my scale this way. I'm going to go ahead and just put that time here. I don't know the time. I'm just going to call it t, but I do know that the speed is 95.3 feet per second. I'm not going to bother getting a ruler and getting this exactly correct. If this is 117, this would be maybe about 60. That 90-something's maybe about there, so I'm just going to put it right there. And again, that's 95.3 feet per second would be that distance on this graph. Okay. Now I'm going to make an assumption about how the car's velocity changed. I'm going to assume that the velocity changed linearly from 117 to 95.3, which means I can connect these like this. That's a little bit of an assumption. May or may not be perfectly linear, but again, if we don't have some sort of assumption, we can't move on with the problem. And it turns out that even if it's not perfectly linear, it's probably going to be pretty darn close, and our results should be pretty reasonable and close to reality, whether this is perfectly linear or not. Now, I'm going to take note here that this is a trapezoid type of area. I'll deal with that here in a minute. The time is unknown. The quantity that we do know is the 250 feet that this car traveled between the initial position and the final position. That's what I would call delta x, a change in position. If you just want to call it like d for distance, that's fine in this example. And what we can do now is we can use our graph to write an equation that will allow us to solve for t. I hope you've seen my videos on how to find displacement. Displacement is found by area under the curve here. This area, I'm going to do this in red, this stuff here is equal to that delta x. So what I'm going to do is use that fact to write an equation here. Now, there's a couple choices here. I could break this into a rectangle and a triangle. I like to just deal with the trapezoid. I think that's the simplest thing to do. The idea is, if I go right in the middle, and I look at this rectangle right here, that rectangle has the same area as the trapezoid. I did not do a good job when I did that rectangle. Let me try that again. Right through that point. There we go. That's a little better. Notice that I could like cut this out and glue it right there. If this picture were all geometrically perfect, that area would match up just right. And the area of the rectangle is just length times width, or the height. Here's the important thing. That height is less than 117, bigger than 95.3. In fact, it's the average of the two. So, area of the rectangle, height, is going to equal 117. I'm going to leave the units off because I'm running out of room. Plus 95.3 over 2. That gives me this red height right there, which remember was the height of this rectangle. Right. Then I'm just going to multiply that by the width, which is t, that we don't know at this point. So you'll notice what I've done is I've used the area of the trapezoid to write an equation which has only one unknown, t. I'm going to go ahead and write this with putting all the numbers in. The delta x is 250 equals, and I better put little NCU for note consistent units, 117 plus 95.3 over 2 times t. And now all I have to do is solve this equation for t. First step would be to multiply both sides by 2. Next line is going to read 500 equals 117 plus 95.3 times t. Next, you could add these together and then just take 500 and divide by that. If you have a calculator with parentheses, just take 500, divide by this quotient. If you solve that for t, I get 2.36 seconds, approximately. Right? So we now know the delta t. I'm going to go ahead and find the acceleration of the car while I'm at it. So remember, acceleration is delta v over delta t. Right? On the graph, it's rise over run. So if I look at this graph, I'll do this in green. Rise over run. That's your delta v. That distance is your delta t. So that's going to equal 95.3 minus 117. I'll put the units out here. Those are in feet per second. And that's coming from v final, right? Final velocity 95.3 minus v initial. Initial velocity is the 117. And then over delta t. Delta t was 2.36 seconds. So what we get for our acceleration, if I work this out, I get negative 6.7 foot per second. Or you could put foot per second squared, would be just fine. I like the foot per second. I think that this is a very good way to represent the units. And what this means is every second that goes by, the car is going to decrease in velocity by 6.7 feet per second. So, point of this video again was how to use a velocity graph to analyze the motion of a vehicle. You know, I tried to make this example just a little bit more complex than the last one, and the next example will be a little bit more complex than this one, and so forth. Notice how I was able to write an equation that allowed me to solve for t by setting the area under this curve equal to the known displacement. So, anyway, hope this video helps demonstrate these concepts. Have a great day.